the button and you speak. talk from there.
All right, if I can have your attention, please. Yeah, okay. Can we quiet down a bit? Thank you very much. Wonderful. Well, thank you very much for being here on this lovely and nicely warm day for the wonderful occasion of a foundation lecture given by Dani Gamerman. Now, I'll say 2 words about Dani, or maybe a few more than 2. He did his PhD in 1987 at Warwick University, which connects us in 2 ways. I did my PhD in 1987 as well, and I'm currently working at Warwick University. But we connect in more ways than one. So Dani's been at the Federal University of Rio de Janeiro since 1996, I think, at least. He's now Emeritus professor there. He has had a major impact on the field through many excellent graduate students and also through his wonderful influential publications in lots of areas, dynamic models, spatial statistics, survival analysis, and a lot more. And right now he's going to talk to us in this foundation lecture about exact spatial analysis via process augmentation. So, Dani.
Thank you very much for you all being here. I would like to first start by thanking the scientific committee for giving me this wonderful opportunity to address you. And I'd like to also thank the organizing committee for putting up a program on the organization and proposing and having accepted a meeting. It is very special, unique, and fantastic city that we are in, inside this wonderful country that we are in, where I have so many friends. My talk is going to be about spatial analysis. I'm going to give you a few pointers to all the names, the words that are in the title alongside it. So the first point that I would like to make is that this is joint work with a few people. On the top line, you have Flávio Gonçalves, Douglas Silva, and Guido Moreira. They were all my graduate students and now my current collaborators. In the bottom line, you have Isabel Nolau, who is my current doctoral student. And then all in statistics. And these 2 guys, Vinícius Peripato is just completely a bright young researcher in remote sensing. And he's a wonderful collaborator in the applied area I'm going to talk to you about, which is between remote sensing, archaeology, ecology, all those areas mixed together into a very nice piece of work that I enjoyed very much doing. Carolina Leves, apart from being a nice-looking woman, she's a brilliant ecologist, and she's more important than that, she's also my niece. So it's very nice to collaborate in family with such a fantastic group. And you'll see just a glimpse of what they've done. I'm just presenting here the highlights of the work that we did together. If you want to learn more, do come to Brazil. We are going to have the Brazilian Basia meeting in December, 2 to 6 December. There are plenty of invited speakers that are here. These people are all going to present their work there, and hopefully the 6 of them will be there so that you can get more information about it. The content of my talk will be a brief introduction about spatial analysis. I know many, probably most of you are aware of the basics of what I'm going to talk about, but just in case some people here are not that familiar, I'll provide you a brief introduction to the subject. Then I'll present you a motivating example that work I did, applied work I did some 10 years ago. And it's going to be good to point out some of the ideas that I would like to develop in the work that I want to do. Then I'll get finally to the aim of the talk. Then I'll talk to you about what is this process augmentation. It's not that complicated, but how it is important to perform the analysis the way we want to perform them. And then finally, I'll reach the main subject of my talk, is the different uses that we've been involved with for performing analysis in different areas of spatial statistics using this idea to get exact analysis. And then I finally draw some final conclusions. So the introduction is just to leveling out for all of us, what are we talking about? We're talking about spatial data, avoiding the risk of introducing spatial temporal data in there as well for the sake of time that we have here. And I would address more focus in the talk to the spatial aspect of the data. So there are three main types of spatial analysis: spatial data, geostatistics, aerial data, and point patterns. And this is an example of a point pattern. Is an area of interest, and what you see, the blur, the red blur that you see, is a collection of small points. There's thousands of them there. And the idea of point pattern is to get data of the location of occurrences on an area of interest and try to extract the signal that comes out of this noisy point to get what makes some regions have more points than others, more occurrences. The talk will be more focused, but not entirely focused on point patterns. You'll see that we are going to make some excursions to geostatistics, and probably you could think, I hope, that's the hope of this talk, they'll do to come up with some excursions to other areas of statistics or spatial statistics, and maybe connecting it to work that you do in other areas outside spatial statistics. I'm skipping the part that is related to time. The temporal domain is excluded, but we have been developing it alongside what we do, and maybe we could leave it for questions or perhaps for another conference. So the most usual models for point patterns, which is the kind of data that I presented you in the first slide, is the Poisson process. Poisson process is very nice for many reasons, and one of them is that it only depends on a single parameter. The complete specification is dependent on a single parameter, but this parameter is a function. So it's an infinite dimensional problem that we have in our hands. The Poissonity implies, as you all know, independence between these joint sets, and it's something to think about, because it will appear later. The notation for a point pattern is this one. For a point process, sorry, Y is the data, is the collection of presences and absences in the area, in the whole space. And the number of points is also a random variable. It is a Poisson random variable, where the mean is the integral, is the integrated intensity function, or is this integral. Okay? And we can identify, sometimes it's easier to identify the observed object, which is the entire process, with its observed locations, the presences of occurrences. There are a few problems here. The first one is that the object that we want to make inference about is infinite dimensional. But the most important problem is the likelihood. The likelihood for lambda, the function lambda, is this object, well known. I think everybody has seen this expression before. If not, there it is. And it depends on the integral of an unknown function. And this, obviously, the integral of an unknown function cannot be directly obtained, so you cannot compute the likelihood. It's not only you cannot analyze, you cannot compute it. Okay? So the solutions that have come out to handle this difficulty, this impossibility generated by the likelihood, is to approximate it. And there are many ways to approximate this likelihood. You can have parametric representations of lambda through kernels, spline wavelets, whatever is your favorite parametric representation. You can use quadrature rules to compute the integral, or you can discretize the region of interest. Okay? So almost all the approaches involving point pattern specification at the completely non-parametric setting that we have decided to tackle are based on approximations. Another issue that must be taken into account, the inherited independence that is in the point process representation is unsuitable for spatial analysis. Spatial analysis is exactly the opposite. It's the analysis we want to benefit from the vicinity between neighboring locations to borrow information across and make more stable and more even smoother specifications. Okay? So we need something else. This something else was already available more than half a century ago, where Cox proposed his model where, in addition to the point pattern representation with the proto process, you allow the intensity function to be random, which is obviously for us is no novelty there because that's what we do. We introduce naturally this randomness through the prior distribution for the function lambda. And one important special case that is very much used in applications is the log Gaussian Cox process, where the log of the intensity that now sits on the rail line follows a Gaussian process. Now, the fact that most people, or many people, shall we say, use this approximation means that they now have a computable posterior. They are allowed to compute the posterior, obviously apart from the multiplicative proportionality constant. But the fact that we are using Poisson process likelihoods, even in the approximated sign case, alongside Gaussian process priors, means that the posteriors that are obtained as a result are analytically complex, and we cannot extract any meaningful summary from it. And we need yet another approximation for extracting information to obtain posterior means, posterior median, credibility interval, and so forth, credibility regions. And there are many options available in the literature. I don't need to tell you about it. We all know the wealth of possibilities that are available for us. So the point I'd like to make is that that means that the resulting analysis comes out as a result of two different kinds of approximations. Sometimes they are presented as one, but really there are two approximations involved if you are using any form of approximated likelihood. The work that I'm going to present to you today is based on a single source of inaccuracy, and the single source of inaccuracy comes from that idea of having to summarize an analytically complex object, which is our posterior distribution. Okay? And the way we chose to do that, which fits very well with the approach that we take, is MCMC. I know it's slow. We don't want to do anything slow nowadays, many of us at least. And I'm going to go a little bit against the tide. And I think in this area of application, most of the examples that come out are not examples that you need to do in your mobile phone, taking a few microseconds. It's analysis that we can certainly wait a few minutes, a few hours, or even a few days. You'll see the examples and you understand. So there is no need for this hurry and to jump into approximated results, some of them with not very well known associated error. So I will try to push as much as possible the border in the direction of trying to do as much exact analysis as possible. Okay? And this we will go back to the last sentence at the end of the talk. The other point that I'd like to mention, just briefly, because it's not in the main direction of the talk, is that we want to put regressor, we want to have better explanation than just describing an unknown intensity function. And there are many situations where we know what is very likely or is possibly likely to influence the intensity function, the variation of the intensity along the space that we are studying. So one obvious way to introduce regression is just build a linear regressor, sorry Nick, linear regressor here alongside, in an additive way, sorry again, in an additive way to the intercept that is space varying to accommodate for the movement, the natural movement of the intensity. We know from many applications that we have performed in just statistics and in aerial data, that spatial analysis is typically an area where you have lots of extra sources of uncertainty, extra movement, and it's not always easy or the best way to go forward to have this separation here, to have this additive sign. And space also creeps in the regression term in many different ways, not only because the regressor may be space varying, but also because the effect may vary along space. It is something that I would like to address with the motivated example in a minute. So we're extending the general form of the basic model by allowing the regression coefficient entirely, not just the intercept, to vary over space. So we have a slightly modified expression for the intensity function as describing a regression term, but it's a regression with flexibility because we are now allowing the regression coefficient to move over space in the basic setup that we are considering. Well, there are a few problems. I wouldn't want to dwell on the specification of the regressor because that's not the main theme. But if you want, I can go back to it. There are differences that must be accommodated if you're taking a regressor that varies only over space, and there are regressors that don't vary over space at all, which are associated with individual characteristics like age, gender, and etc. And we need to handle it in a slightly different way that does not impact anything that I'm going to talk to you today. Okay, so I don't want to go too much into that, other than saying that one possibility that we have been exploring in such cases is that when you have a fixed covariate like age, fixed over space, then we might like to use a space varying, let me go back. When you have a space varying covariate, you use a fixed regression to avoid identifiability problems that may come up in the product of two function moving over space. And when you have a non-spatial covariate, we may then be allowed to use space varying coefficients to accommodate for the flexibility that comes out, that spills over from the intercept. He's not capable to handle all the spatial variability, typically, in many applications. So this is model presentation that I'm going to use as a base for this presentation. We have the likelihood, and then we have a link function relating the mean function of the intensity function through covariates, or just to the intercept if you don't have covariates, and then you superimpose a multivariate Gaussian process for as a prior for the beta. And then you also have other known quantities, which are usually the Gaussian process specification hyperparameters. The motivating example came from another PhD, a doctoral student I have more than a decade ago, and brings us back to the picture that I presented to you as an example of point pattern. The area that you are seeing there in front of you is the map of the city of Rio de Janeiro, and each dot that you see, and there are 18,000 of them, is the home of somebody who died from a cardiovascular disease between the years 2002 and 2007. And we want to know what makes some areas more susceptible than others, and what is affecting the intensity there. Now, in this problem, this is a typical epidemiological application, and most epidemiological applications are based on aerial data because health policies are not based on a location-specific decision, but is rather organized in terms of areas like administrative regions, like in Italy or in Rio. So in this case, it was okay to use discretization, and then that's what we did to get the analysis done more than a decade ago. The only point I'd like to draw from this example, there's plenty of interesting results from this example. I want to show you one of them to emphasize the point that I want to bring today now. This is the result of the estimation of the age effect. Age is very important for cardiovascular disease, I'm sorry to say. We are sorry to know that cardiovascular disease is more common as you get older. And as you can see, in all the results obtained here, this posterior distribution is very comfortably located above 0. But the result of the analysis, first of all, this very thin shaded area here is the effect that you obtain if you use a fixed regression coefficient. And these bars are a kind of box plot of the estimation of the 33 administrative regions of Rio, and the mean, the posterior mean, and the posterior credibility intervals at 95%. And then you'll see there is a lot of variation. There are very interesting variations. It separates the rich from the poor very vividly. If you're poor, roughly speaking, if you're poor, it doesn't matter what your age is. If you're rich, it does matter much more. Anyway, the only point I'd like to make here is the relevant spatial variation. As you can see, it varies a lot depending on the administrative region of Rio your house is. Okay, so this is my goal. I would like to do this analysis, this kind of analysis, not forcing the data to be restrained to administrative regions. I haven't reached that goal yet. I can give you this spoiler, but I'm going towards it. And I haven't reached it just because of the size of this application. There are 20,000 observed locations that we need to worry about. So the aim of this talk is to answer the question, can inference respecting what we specify in the model and not without having to approximate it be made? And the answer is yes, we can. And this talk will present a few examples of this exact analysis, what's so-called exact analysis, in different areas of spatial statistics. But first, I will not talk to you about what is the process of augmentation that is crucial for us to being able to perform the exact analysis. And this is a paper that came out in 2018. This, in fact, was presented at an invited session at the Edinburgh ISBA meeting. So I don't want to go back there again. The paper is long gone, and the presentation was 3 ISBA World meetings ago, so it's old. But anyway, if you haven't seen it before, it's nice to see it. We cannot solve the intractability of the likelihood directly, obviously. We cannot integrate it out. We need to approximate it or trying to find an alternate route. And the alternate route was proposed a long time ago in this paper by Lewis and Shadler, and this is referred to as Poisson thinning. So it describes the algorithm to simulate from Poisson process with any unknown form of the intensity function. So the way to do that is first to set up the upper limit of the intensity function. So you have to pay a price. The price you have to pay is to assume that the intensity function is bounded. I don't think this price is too much to pay. If you think it is for your particular applications, then you cannot use what I'm going to talk to you right now. But I think many applications can get by very well by assuming there is a finite limit. So now we augment the process that we are analyzing, the y, by x, which is a Poisson process with an intensity function which is constant, so it's a homogeneous Poisson process with intensity given by the bounded value of the intensity. And to sample from this process, all you have to do is to sample the Poisson number of observations. We know it's Poisson, and because the integral is very easy to evaluate because it's a constant intensity. And then you sample it, and then you get all the points, and you distribute them uniformly over the entire region. So it's a very easy way to sample from this homogeneous Poisson process. And to sample from this varying intensity function, all you have to do is retain each point, each of these capital K points, and you retain with this probability proportional to the intensity. The higher intensity values are more likely to be sampled, and the low intensity are more likely to be discarded. And I would like to mention to you that after this specification of X, Y, the remainder process is also a Poisson process, conditionally independent of the data that we are observing with complementary intensity. Okay? This algorithm has an analytic version. The analytic version is a joint distribution of the data and the augmented process X, augmented by the Y, here I call Y tilde, the augmented part of the process. The augmented process is X, and the joint distribution that describe this data follows exactly the algorithm. You sample K, then you sample X from K with this uniform, you sample K from the Poisson, and you have the acceptances and the rejected ones represented in this expression. That's the likelihood, the exact likelihood for the augmented data. Now, a few important features here. First, the integral disappears. We can compute the likelihood for any lambda that you like. Any lambda that you can think of, you can obtain the likelihood. And the second part, which is technically important, is that the likelihood does not depend on the entire uncountably many locations. Just a finitely many of them are required for the evaluation of the likelihood. Okay? So this idea we saw, I'm not going to claim that they were the first to propose it, but we saw it in the paper by Adams et al., based on the thesis of Ryan Adams that was a Savage honorable mention, I think, some few years back, supervised by Murray and Dave McKay. So, but we made a number of important changes to make this work. I don't know if Ryan Adams is here, but if it is, it's great work, but we changed it in many different ways. But the idea, the basic idea, we saw it there. So the only change to the model that I previously presented you was that we need to include the supremum, and then we use a function. The link function must be bounded to 0, 1, otherwise this would not be the supremum of the intensity. Okay? So there are many options here. You can use the probit, the logistic, and other possibilities are available. We have worked with probit and logistic because they provide nice ways to perform the step of the extraction of information via MCMC. It gives us very nice MCMC. The inference that we obtain leads to smooth estimation, unlike some of the analysis with discretized. And I'm talking about discretizations where you have thousands of grid cells, and even then you see a not very smooth looking outcome. And we put Gaussian process because we want smoothness. The MCMC that we propose is mostly based on Gibbs steps, and it was quite efficient in the sense of going fast towards the stationary region and having good mixing properties. Okay? So this is all part of so that's the basis, the foundation of this foundation lecture is that paper. Okay? Now I'm going to start the talk. So I'm going to talk the recent work that we have been doing exploring this idea. in many different scenarios. And the first one, surprisingly, is not point pattern data. It's for just statistics. This can also provide useful solution for problems in geostatistics. I'll tell you which in a minute. This joke with Douglas, not published yet. But you can find it in archive if you are interested. So the basic geostatistics setup is based on measurements Y that are made over measurements with measurement errors over an unknown surface that we assume to be smooth. Typically, that's the situation which we call S at location X. So we have 3 objects, possibly random, and the joint specification is by this decomposition, and this part of the decomposition is normally thrown out, only retaining the S part, because typically X is known, or if it's not known, if it's random, it has randomness that is not associated with the underlying process that we are interested on. Okay? And the main goal in this situation in geostatistics, as you all know, is to predict measurements at locations that have not been observed before, so that you can get better usage of your exploratory oil field or whatever. The standard model is written in this way, where you have Y having S as its mean, you have the random error nugget effect in the area, and then superimposed on top of it is the Gaussian process specification. We don't need to worry about X in the basic geostatistics setup. Now, the problem is that sometimes data collection is not as we thought it would be. And for example, it's very reasonable to have your choice of locations associated with the process you are interested on. You may want to get more points where you think the oil content is larger than where you think the oil content is lower. So there are reasons to propose a sampling scheme where you have preference in a sampling. So X cannot be discarded from inference, and then you have this extra component here getting away from the basic geostatistics setup that many people use nowadays. So this model was proposed, one of the models to handle it was proposed by Peter Digo, Raquel Menezes, and Sue, 2010, a model that I like. I think it expresses very well what we want, where we now have the randomness associated with X being described by a point process representation, where the intensity now is a function of this underlying surface S that we don't observe, but we'd like to make inference about it, because that's what we need to get inference about the unknown unobserved locations. Okay? So what they did is to use, just like the Log-Gaussian-Cox process, they allow the log of the intensity to be a linear function of the surface. Okay? What we did is, following the recipe of the main model, is to allow it to be described in a slightly different way by introducing the maximum and the transformation that obeys the restraint it has to. They use approximations, and we use the exact methodology that I just described to you. Okay. I'd like to think, I didn't speak to Peter or Raquel about it, but I'd like to think that what we are proposing, I think is what they would have liked to have proposed. And so I'd like to think it that way anyway. So we did some simulation exercises, and the 3 scenarios are where the intensity affects the intensity, the underlying surface affects the intensity via log link, as most people use, or a probability link, as we use, or scenario where there is no preferentiality. We generated a number of replications of those 3 scenarios, use different criteria for evaluation of the quality of the predictive performance of the model. Okay, so EPS stands for exact proportional sampling, which is our model. DPS is the discretized version, similar to what we use in the motivating example. NPS is the standard geostatistic setting of non-proportionality of sampling. And then following the reference suggestion, we use an alternative model based on INLA. There is a nice book on INLA by, online book, by Elias Krainsky and co-authors. One of the chapters is devoted exactly to this issue. And so we use that as comparative, the issue of proportional sampling. Okay, so I don't want to spend too much time. So our model should do better here, and it did. The non-preferential model should do better here where there is no preference, and kind of did alongside ours. Ours didn't do that well, that bad. And the log link is where the inlet should do, because that's the model that they are using. That's not the model that we are using, the link, at least, of the model. And I don't know if you can declare any victory here to anybody. So the main summary from this simulation exercise is that our approach did well, at least as well as the other ones, to handle it. So real data illustration, we analyzed two data sets that are very common in the spatial statistic literature. I think they are in SpatStat. And we have measurements and we have predictive points. And again, our model did just as well as the basic geostatistic model, which is something that we find it interesting, at least, and better than the other one. And then we have another data set. It's lead concentration in plants in Galicia to measure the pollution. It's a well-known data set if you're working in spatial statistics. I think it's also in SpatStat. And we did this interpolation. We did interpolation. We did cross-validation exercise. We're just leaving one out. I know there are better schemes for doing leave one out exercises in spatial scenario, but just to give you a rough idea, we use leave one out. And again, our model did considerably better than the other one. And by the way, these other ones are all based on discretized. The DPS, NPS, INLA, they all work in the approximated likelihood scenario in different ways. The second area of application, how are we doing?
12 minutes.
Good. Oh, plenty of time. Good. So I can spend some time. This is an area that I've grown very fond of in recent years. This is associated with the work that Guido Moreira did in his doctoral thesis. Appeared a couple of years ago. Now, here are examples: eucalyptus in the Sydney Bay Area, or angico is a tree, a nice tree that is used for. It has some uses. I don't want to dare. Maybe there are some people with a college background, and they would say, "No, it's not like that." It's used. It's useful. So. Here, what happens with presence-only data, and this is a feature that is very common in many areas. We don't like it. We in this room, we want to sit comfortably getting our case control comparisons, and life or parts of science are not like that. And we need to be able to answer to these questions. So this is an important area in many applications where only presences were observed. People go out in the satellite, or in planes, or in ground excursions, and they collect data, and they just register what they see, without much scientific preparation for marking presences and not counting absences. So that's a feature of many ecological and anthropological data collection exercises throughout the world. So we have the latent process, the augmented latent process, but now our occurrences, which I'm not denoting by Y anymore, I'm denoting by Y bar, it's also a latent process because it hasn't been completely observed. We have only observed some of the occurrences, not all of them. Our data is the observed occurrences. So the occurrences are latent, and they are driven by some covariate specification. We use the logic transformation here. We could have used the probit or whatever. Okay? But our data is Y, as before, but has another component, because it's a component associated with being able to observe the occurrences that are there. And it's not easy. You may think, why don't they go around and circle it? We are talking about a vast area of 2 million square kilometers, or in the case of the Amazon jungle where we are going to present the work, it's 7 million square kilometers of dense forest. It's not easy to go about by ground, by satellite, or by airplane and make a complete sweep over the entire region. So we need to be able to provide results from this incomplete data collection process, because that's what it is. That's what we have in some cases. Okay, so this extra component associated with observed occurrences is described again after logic transformation by some other covariates, the observability covariate, what makes some regions being more observed than others. And again, we have, like I showed you before, the unobserved occurrences, and they are the complement with respect to the Y bar process of the entire occurrences. They are the complement by getting what has not been observed. Okay? So we have two regressions here. One associated with the intensity of occurrence, as we were doing until now, and the other one associated with observability. And the observability has nothing to do with nature itself, the way we are part of nature. But we collect the data, we are able to obtain the data. We, I mean humans. We show that in some cases we could separate, it's an important issue that we be able to separate the effects of the observability and the intensity, and maybe if you can separate them, you can put even the same covariate, and there are reasons to include the same covariate in the two components. And also another nice feature of our model is that we can draw the map of observability. We can then extract and get information about the probability of observing. The feature of interest in these cases are trees in different areas. And here's a tribute to my colleague. We used to our colleague sitting in the reserved seat that we are using his ideas and the sampling associated with the logic transformation there. It works very well. Now, to assess the effect of what he did, we compared against the standard practice, which I think is using the traditional IPP, inhomogeneous point process. And they in this area, in ecology and in anthropology as well, and probably in other areas and in botany, whatever, I don't know. But in applications we've been involved with, they use as evaluation of the effectiveness of a model, the area under the curve of the receiving operating characteristics. I must confess, I don't know very well what that means, but that's what they use. And this is a mathematical object. Anyway, and these are the results. In the case of the eucalyptus around Sydney Bay area, there was an independent sample of presences and absences, and we used that as a evaluation exercise. And the area under the curve is a function of the parameters, so it's another parameter, so we can get the posterior distribution for it. And here's the mean of the posterior distribution. And if you use the traditional approach, the area under the curve that you obtain is lower, very close to the naive representation. It's almost like tossing a coin to this side. 5 minutes. Okay, so I managed to waste my time. It's amazing. Anyway, we got good results, and then we have this nice result that we are 90% sure that we are better than the other ones in the competition. I want to spend some time in the pre-Columbian earthworks in Amazonia. It's a paper that just came out in Science, wonderful magazine. I won't spend my time, I will have to control because of time constraints. We want to see what's the effect of the previous human presence in the jungle. And there were 960 interventions on Earth. I won't go into much more detail than that. And they were obtained in this not way that we would have liked. Well, let's keep the relevance of science. It's enormous. The paper appeared in more than 200 news outlets around the world in all kinds of language because of our analysis of this data set. And then we have the results of the regression that we use to explain what makes some spaces being occupied more often than other ones, and whatever. But I think what got better from our results is that we can draw a map of the probability of occurrences and around the region. And we did the analysis at a 1 square kilometer pixel, and there are 7 million of them. So the data set is huge. Anyway, the picture that was the best picture that I think we got from this is that our analysis allowed to obtain something that there are other ways to analyze the data. Then they are a struggle to get this picture that for us Bayesians is extremely simple to obtain, which is the number of unobserved earthworks. What is still there in the jungle that we have not observed. And then we did obtain, it's just a predictive distribution of the data that has not been observed. It's just a parameter, if you like, of the model. And here we obtained these nice results. And I think what got the paper accepted to Science that our credibility interval, our very basic credibility interval, has a lower limit of 10,272 for the number of, which is 10 times more what has been observed so far, even with all the invasion by us post-Columbian humans in the area. There's a lot more in there. And that there is a lot to talk about it. I just wanted to give you this, to show you the result. I'm having an issue on a short text that will appear in the September issue of Significance, talking about the relevance, and there is a paper on Science if you want to learn more about it. Finally, the last point I'd like to make is work still ongoing is with the PhD students. It's just completing, well, hopefully, completing by now no, I shouldn't complain about her. She's working hard. I don't have many complaints to her because, as you see, it's a tricky problem because we all use Gaussian process representations because we think that the intensity function is smooth, but real life presents us discontinuities, all sorts of non-stationarities that are not contemplated by the usual isotropic Gaussian process representation that most of us use in our work. So there are many alternatives that have been proposed, mostly from the geostatistic literature. There are some papers there that don't have time. And the route we took was the partitioned into local Gaussian process. We divide, instead of considering naively and wrongly, there's just a single Gaussian process putting smoothness all over the region of interest. It's stupid to think that this would take place, this would hold in an area like the Amazon jungle, for example. Anyway, so we split it into regions, and we build a model that involves replacement of the data by a collection of capital L areas under which the stationarity holds. And then we allow randomness to decide how smooth we want to be the interrelations between the different areas. And we can also use this specification to cluster the data, if you like, if that is your objective. We can also talk about efficient computation with where you can use local inference to take care of the computation cost and be trying to go fast if you want. Okay, -1 minute. Okay, so I just want to go flashing through the slides with very preliminary results. This is data that was generated artificially with our equal to. And here's the very nice non-parametric estimator of DIGO. Here's what we get by reconstructing the data. We got the smallest mean square error in the estimation, and if you can divide the computation into areas, you have a lot of gain. As you can see here, you can draw 90 iterations from one iteration by considering just a single area. We can estimate, and here you can see, I don't have time, you can envisage some empirical evidence of how much we lose by analyzing data into smaller areas than using a single analysis through all the areas. If you want to cluster, you can cluster as well. This is a basic clustering. And then if you want to go Bayesian in your clustering, incorporation the uncertainty, that's the picture that you get as you move along the values of the number of areas you are considering. There are going to be some nice sessions this afternoon about clustering. Concluding remarks. Our approach doesn't approximate point pattern components in your model, unlike many other approaches that you probably may have encountered in your field. Temporal extension I mentioned, computation, we haven't parallelized yet, but we will. This will speed up things, especially considering that we are dividing the areas. In the last part, it's very important to do that. There is everywhere you use Gaussian process as a process problem in the matrix operations with Gaussian process. There are many ways of handling it. I don't have time to go through that. We need to improve about regression because I want to go back to my cardiology death data from Rio. We have software, we need to improve more. We have software only for the presence-only analysis, software developed by my student. And the summary of my talk is exact is better than approximated. Thank you very much. Now, you noticed a line that I put in the bottom of one of my slides. Let me greet you with some Brazilian folk song where the line was taken from. Let's see if it goes. No, I didn't. Oh. That's okay.
So despite all that, we still have a few minutes for questions. If there are any questions from the floor. Yes? So, yeah, there are microphones going around, I think. So.
I have a question. For example, in the example of the trees, the forest, there is one characteristic that the canopy of the tree prevents other trees to grow under it. So you do have some kind of exclusion there. Can you take this in consideration? Because then the Poisson process is not very good.
No, yeah. You need some other process where you have ramification and consideration. You need to go away, so it may happen.
Can you handle this with your method?
Not with these models. I need another model.
Okay. Thank you.
Yes? Over there.
Thank you very much, Dani. Wonderful talk. So exact is better, and the question is, what if you actually need to do online inference? If you would like to, for example, update your inferences in real time when a new data point arrives. Is there a quick way to update?
No, there isn't. And this was my point, is that this kind of analysis, all the examples that I presented you, which are, I think, a fair representation of the area, they don't need to jump into conclusions right now about what happened 5,000 years ago. And, or even the other ones, the current ones, they don't need an answer at this very minute. You can wait. You can certainly, all the applications that I presented you, maybe I have a biased choice of examples, but all of them don't need this fast reply. So the answer is no. If you want to, you have to pay a price. Either you pay a price by being exact and performing operations, your analysis in longer time, or you have to pay the price of approximation. And there is a price to be paid by that as well. That's my point.
So there's one more there.
Well, we have a model that is a valid model for that is used in the area. So, not sure we are. If you have a valid model, I think I'm safe. I would say so. So, I think I'm obeying all the principles of good probability accounting.
I have a question. Thanks for a great talk. My question is on the lambda star, the maximum. If you have a very inhomogeneous Poisson process, my experience with the Adams and Murray algorithm is that you're going to sample a lot and you're going to have to waste a lot of points. And personally, I moved away from that because I found it too inefficient when you've got highly inhomogeneous Poisson processes. Do you have any experience with that or any problems that you encountered?
Well, I'm not sure I understand the question very well, but let me show a picture from my garbage part of the talk. Now, you never know. Where is it?
You never know. You might end up having more time than you think, right? And
let me see. No, it's not here. Ah, here it is. It is here. You can, as you can see from this picture, I won't go into the details, but you can, if you divide the area, and you can get improvement. I didn't present it because this was a part of my presentation 6 years ago in Edinburgh. I presented it there. But if you do this splitting, if you have a large variation in the